Okay, so it's going to be 3.2. We're going to look at functions, relations, and domain of functions. Sometimes a difficult task to take a look at, but just remembering that the domain is all the possible x values that we can input into a function. So we can put it in and do a calculation and get a real value. So we're going to see there, for at least at this part, there is only going to be two types of calculations that are going to restrict the domain, remove some x values that we can use. Okay. So we did this with the previous function, the box one. We had one input, and that was the amount of the cut, because that would change it, and as we change that cut, it gave us a change in the volume. So we call that the input variable, and the volume would have been the output variable. So in that case, the domain was limited by the physical constraints of the paper. So if the paper, the shortest width was 8.5 for that paper, the biggest cut we could make, the domain really went from a cut of 0 to a cut of 4.25, half of that length. That was the domain we were working with for x. Any other value of x didn't make sense physically. Okay, so and again, we could come back here at 1.5. We could plug in the 1.5, do the calculations, and we'd see that it has 66 cubic inches. And I think, again, a typo here. This should have been 3.1. Obviously, that's what they're plugging in. So this number here is incorrect. I was going, why did they want to do that twice? Okay. So this is our function we were working with, and again, mathematically there was no restriction to the domain. X could really be anything that we thought of, but in the physical world, anything bigger than 4.5 would not be possible. So is it possible to reference the value of v when x is 1.5 without calculating its values? Yeah, we could do the equation. We could also look on the graph. Sometimes they ask too many questions. Okay, so what does f of 1.5 represent in this context? Well, it's telling us that in this box problem, an input of 1.5 means a cut of 1.5. X is 1.5, and so f of 1.5 is actually, as we read this, f of 1.5 is actually the output. So that would give us the volume, right? It represents the volume for a cut of 1.5 inches. Same thing, f of 3.1 represents the volume of a box that is created by cutting 3.1 inches off of the corner. And if we subtract these two, this will represent the change, right? Because remember, we talked about change as always being subtraction. It would be the change in volume between going from a cut of 3.1 to 1.5, so two different boxes. Obviously, you can't do that cut on one box. This would be two different boxes. So it's a change in the box's volume. And is it, if 3.1 was larger, then we would get a positive value. If 3.1 is smaller, then we get a negative value. So that helps us determine which one is greater, right? If we get a negative value, we say, okay, 1.5 was greater, and then it's going to decrease as we cut to 3.1. If the volume at 3.1 was greater, we would get a positive value, and we would say that the volume was greater. So as we look at function notation, every function notation, when we do f of x, the letter f itself is the name of the function. We could use g of x. We could use any letter we want, but that's our name. inside the parentheses gives us what variable we're using for the input variable. So usually we use x, and then it'll be equal to an output variable, which usually is assigned as y as far as graphing calculators go, but oftentimes we also give it something more meaningful like v for volume. So those are the pieces that we use when going through a function. So what is the independent variable? The input one is the x, because that determines everything. Whatever cut we make will determine the volume. So the length of the cut, x, is the input variable. What does f of x represent? Well, that represents the output variable, or the volume, right? The volume that we get when we make a cut of x inches. What does f represent? Well, that's the name of the function, right? That's all it is. F is the name of the function. Could call it something else. What is the domain of f? Again, x, the domain could be anything, but since it's connected to a context of a piece of paper, the largest x could be is 4.25, because then that becomes 0 there, right? So, and the smallest is 0. You can't make negative cuts. And so we would say our domain, practical domain, is going from 0 to 4.25. And we kind of see that here. And we can find all these other points in between. Again, we have been doing this. So as we graph it, when x is 3.5, f of 3.5, that's the y value. And again, we could look that up. We can find the value of the maximum volume, which appears to be about 1.5. Actually, maybe a little bit bigger, but we go through, we can see the cuts at when the output, when the volume is 40, we could say y equals 40 like we did on the Desmos last time, and then we could find these intersecting points, and that would tell us what size cut we would need to make if we want to make a box with exactly 40 cubic inches of volume. Okay, so we evaluate f of 2 and describe its value. So plug in 2 for x. We do the calculation, we get 63. That means it's got a volume of 63 cubic inches when we make a cut of 2 inches. Okay, and so then we could show that at 60, that could happen at here, get a cut here, or a cut here. 63 was up here, so but for 60 we would draw the vertical line there. Okay, and so we see 2 places that works. We get a volume of 60 for 2 different cuts, and that makes sense. Okay, the boxes will be slightly different shaped, but they will have the same amount of volume. Of course, the one with the bigger cut, 2.1, will be taller, but its base will be smaller. So to go from 2 inches to 3.5, how do we do that? Well, we're going to subtract the volumes. So f of 3.5 minus f of 2. So the cutout increases from 2 inches to 3.5 inches. But again, what you see is actually it increases negatively, so it's actually decreasing. But the change of volume, f of 3.5 minus f of 2. Okay. So every function we talk about, there's an input which goes is connected to the domain. Input, again, we will always use x, and the domain are all the values we can use in that context. The range are all the possible output values. So in our last example, that would be the volume of the box, and again, the volume of the box went from 0 to some maximum value. And then there's also the rule, which is actually the function itself. It's which we probably refer to the function. It's the multiplication, the addition, the subtraction. It's the mathematics that gets done. So the rule is the equation that we usually think of. Okay. We can do it with words. We can do it with algebra. We can also represent it as a graph or table of values. Those are all ways to represent a function. Sometimes the easiest way to see the mathematical relationship is with the algebra. We can see whether we're multiplying or dividing or subtracting. The graph, we can see more visually the difference, the change, but there's multiple ways to look at a function. Okay, so we always write, so if we speak about a function f of s, so s is the input, so it's f of s in terms of s, so the in terms of is telling us what the input variable is, f of s is our output. So it's always the output in terms of the input. And the input value is always independent value because the output will depend on whatever changes we make to the input. Okay, so we can reference a function using a name. So we might talk about the perimeter of a square. Perimeter of a square is 4 times s, the length of its sides. So because there's 4 sides to a square and they're all the same length. We could also reference this as a function. We could give it a name, f of 3.2, and that would be the perimeter of a square that has a length of 3.2 inches. Okay, and then we would somehow reference back to that formula. So what would f of 5.8 represent in this thing? Well, it's going to be a square that has a length of 5.8, and this function has been set up to represent the perimeter. So we'll take 5.8 times 4, and that will give us the perimeter. So given the square's perimeter cannot exceed 48 inches, that's talking about an output, right? Because it's talking directly about a perimeter. That's a range. So then we're saying, well, if it can't be more than 48, well, then what are we going to have to do? We're going to have to, what could the side length be? Well, instead of multiplying by 48, we divide, instead of multiplying by 4, we're dividing by 4 to see what the side could be, right? So looks like the biggest the side could be would be 12 inches. Because if it's bigger than 12, then the perimeter is going to be bigger than 48. So we got to keep it less than or equal to 12. And so sometimes we can kind of do that. We're using what we would call the output or the range of 48. That 48 is the maximum for some reason. So the domain would have a maximum of 12. So there's a connection between what the domain can be and what the range can be. Given that the square's perimeter cannot exceed 48, what are the possible values that the perimeter P can take on? Well, we know that 48 is the maximum, but since it says it cannot exceed, it can be smaller, and I guess, we could go all the way down to a perimeter of 0, because if you have a length of 0, so that's kind of the very smallest that you could go. I don't know that you could call that a square if it has side lengths of 0. So I don't know. I would personally not put equal to, because that's not a square. It has to have some length to it. But that's just my thinking. Okay. What is the rule that determines how s and f of s are related and change together? Well, it's 4 times s or f of s divided by 4, right? So there's these two types of relationships. The relationship is we take 4 times the side, and then that gives us the perimeter. And this is so could there be more than one value, more than one perimeter if I had the same value of s? Well, think about it. Whatever s is, we're multiplying by 4. That's always going to give you the same answer, isn't it? So there will be exactly one value of perimeter for every side length. So now let's take a look at this. We've got a problem we're going to consider. Billy is walking from the front door of his house to a bus stop, which is 960 feet away from his front door. As Billy walks out his front door, he walks in a straight path towards his bus stop at a constant rate of 7.5 feet per second. So this is going to be continually reduced by 7.5 feet per second. So one way to think of this is we can use t as the time. So 960 is the maximum distance away since he is walking towards it. And then every second we're going to be subtracting 7.5 feet. Right? So as he walks, we're going to have 960 minus 7.5 t. The distance is going to be getting smaller and smaller. Okay. To find a function h to determine Billy's distance from his bus stop, well, 960 minus 7.5 t, where we could think of the function h, h of t, as being the distance. And again, we could use anything else. We didn't have to use h, we could have used g, we could have used b of t, so bus stop or something. Anyway, they're using h. What is the independent quantity? That's time. Time is so we're measuring that. That's your input, the amount of time. And what you can see is that you'd have to do a calculation, but once you get to 128, you're at the bus stop, and that's where you stop. The dependent quality is the distance from the bus stop, right? It's the h of t. Depends on how much time has gone by, so the distance will change from, it actually changes from 960 all the way down to 0, but we always list intervals from smallest to largest. But in the story, he starts 960 away, and as he walks, as the time passes, he gets to be where he's at the bus stop. So what do each of the following represent? So h of 0, again, remember the input is time, so after 0 seconds, this is where he's at after 0 seconds, at his front door, 960 feet away. After h of 60.25, this is where Billy is after 60.25 seconds. Those are the two things. If we want to use function notation, Billy's distance from the bus stop after he's walked 23.6 seconds. So that's just simply h of 23.6. Now we could plug it in that formula we had, and we could actually calculate what it is, but this is the function notation for that. And then the change of distance from the bus stop as the time increases from 35 seconds to 48 seconds. Again, we subtract h of 48 minus h of 35. Okay, so when the question is increases from 35 to 48, we subtract them in the reverse order that it's been asked in. T represents the number of seconds since Billy left the door. Solve h of t equals 150. So this is telling us how much distance is left to the bus, right? It's 150. So how long did it take him to get to that point? Well, we need to set up the equation, 960 minus 70.5t, 150, and then solve. So we would subtract 960 from both sides and then divide by negative 0.75. And what you find out is that 108 seconds needed to have passed for that to happen. Okay. Or what they did is they added the 7.5t to both sides. It looks like they subtracted 150. So however you want to solve, but get t by itself, we find that to be 108 seconds. So the vertical intercept is that's our y-intercept. That's the value when, that's the output value when the input value is 0. So whenever x is 0, that's our vertical intercept. Okay, so it's generally the place that the story starts, right? If the input is time, time 0 is usually the start of the story. So if f of 0 is equal to negative 25, the vertical intercept of f is negative 25, and we'd have this point 0, negative 25. So whenever you have an x value of 0, you know you're on the y-axis. you're on the vertical intercept. Okay, so now we're defining h, some function h of x, 39 minus 65.x. It's a distance in meters that a tortoise is ahead of a hare in the terms of the number of seconds x since the start of a 100-meter race. So we could construct this graph. What we're going to see is, though, that this 39, right? Because if you plug in 0 for x, this becomes 0. 39 is our vertical intercept. So that helps us in graphing this. We're going to see a point up here. And then what's happening is it's got a constant rate of change and it's decreasing, which means the distance between the lead is going down. Okay, right? The distance that a tortoise is ahead of a hare in terms of the number of seconds. So generally the tortoise gets a head start because the hare is taking a nap, and that's how that happens. To determine the vertical intercept, well, we plug in 0 for x, vertical intercept has to be 39. Okay. So the horizontal intercepts are where y equals 0. And again, a lot of questions that we do, we're throwing a ball up in the air or something, the x-intercept is sort of like represents the ground because the y may represent height. But whatever it's representing, the x-axis, the horizontal axis, is where y equals 0. The output is 0. So what we call that also is a root, because if you think of the x-axis as being the ground, as it goes through that, it becomes a root. We also call it a 0 of the function. We do not call the vertical intercept a 0, we call the horizontal intercept a 0. So when they're talking about a 0 of a function, they're specifically talking about what x value will give a y value of 0. Okay, and again, these are a little bit harder to solve because we have to solve for the x value that yields a y value of 0. So they give us an example of a function here, h of x equals x times x minus 7. So we've got multiplication going on, and what we take advantage of is there's a mathematical principle that the only way to get 0 when you multiply two things is for one of them to be 0, or possibly both. Not necessarily both at the same time, but as long as one of them 0, you always end up with 0. So 0 times a million is 0. 0 times 2, still 0. So what we do is, since we're multiplying, we can separate this off, that either x itself is 0 or x minus 7 is 0, and when you solve that, you get x equals 7, right? Because you add the 7 to both sides, and so we get our two roots. We call them roots, we call them zeros, we call them horizontal intercepts, we call them x-intercepts, all these things that we call these. Okay, so we're going to go on with the same context, the tortoise and the hare, using this same function, and we want to solve for where the x-intercept would be 0. So, and again, in this context, what does that mean? Well, since h represents the distance between the hare and the tortoise, right? It's how far the tortoise is ahead of the hare in terms of number of seconds. When we find this x value, that's where they're going to be equal, right? The tortoise is no longer ahead of the hare. And so what we do is we set it equal to 0. They added 6.25 to both sides, and then divide by 6.25. That's a perfectly fine way. So they find after 6 seconds, they're equal to each other. There is no lead. Okay, the hare has caught the tortoise after 6 seconds. And we see that on the graph as an x-intercept. After that time, the hare is ahead, so that makes the lead of the tortoise become negative, right? Because it actually means the tortoise is behind. Of course, if it was only like 5 seconds left in the race, it's okay. The tortoise still won. Okay. What is the root of h? What point represents the horizontal intercept of the graph of h? we found all of that. Well, the root of h is 6 seconds, right? X equals 6. And when x is 6, y is 0. Okay, that's a 0. It's a root. It's a horizontal intercept. And we could do the same thing with each of these. And again, all we do is to find the horizontal intercepts. We set each of these equations equal to 0. We can also do it by graphing. And we can use Desmos. Let's go ahead and do this first one here for x minus 6 plus 2. So let's get rid of these guys. We'll just go with y equals 4, what was it? X minus 6 plus 2. X minus 6 plus 2. And then notice with Desmos, the nice thing I like is if you want to find the x-intercept, you just click on it and it'll give it to you. It also gives you the y-intercept. So if you needed that, you've got that. But our x-intercept, which what they were looking for, is 5.5. The other way you could go about doing that is you could actually set it equal to 0 and then do all the algebra, and notice, look, they got the same answer. X is equal to 5.5. This was the same thing. I think we will find that it's we got a horizontal intercept at 4.25 because that's when the volume ended up being 0. It's also, yeah, you plug in 4.25 and x value 4.25, you get a 0. You also get a 0 at 0, okay, and then we get another one at 5.5, which would happen at this part, right? You solve them all. So actually, I guess I should have left that up. Let's go ahead and do that one real quick. Because it's cubic, right? X times 11 minus 2x, 8.5 minus 2x. So we see here is where we stop because it really doesn't make any sense to have negative volume. But if you were able to, it looks like, and see, this really, again, makes no meaning because we've cut so far. But again, if we just analyze this mathematically, yes, we do get three zeros, 3 roots, 3 x-intercepts. Okay, so for this graphical representative relationship between x and y, now this would be sort of like a square root function, except usually we don't get this bottom part, we bring this out. This is not a function because it doesn't pass the vertical line test, right? But this is a relation. So each input value of x is assigned or paired with 2 or more values. We conclude that this is not a function, right? Doesn't pass the vertical line test. Maybe that's what they're going to get to. Determine if f is a function of y. Justify your answer. Well, is x a function of y? No. Is y a function of x? Actually, is x a function of y? Well, yeah, I guess if you were able to turn it over, then you would see each value of y corresponds to only one value of x. So we could say, yeah, x is a function of y, but we're always interested in y being a function of x. It's just the orientation we've taken. Okay, so that the domain of all possible values for a quantity is that's so all input values is what we call the domain. Sometimes with the context of a question, we restrict the domain. But one thing we always work with is when we have a square root function, right? We can't get the square root of a negative number. It's an imaginary number, but it's not a real number. So that's one problem. The other problem is when we have division by 0. That does not give us a real number. It gives us something like infinity, but infinity is not a real number. And then in another thing, we look at the context, like cutting out the box, and when we had a width of 8.5 inches, the biggest cut we could do was 4.25. So that limited what the domain could be. Okay, so what would be the limiting value here? Well, x can't be 0 because we can't divide by 0. That's the only thing we have to worry about. So x is not 0. We use what we call interval notation. It means x can be anything but 0. So it can go from negative infinity to 0. This parenthesis means that 0 is not included. So we just include it on this side, and then we get to the other side of 0, then numbers bigger than 0 to infinity work. If we graph this, we see that the same thing is true for the range. The range is usually we need to look at a graph. So let's go ahead and do that. So we see this, that x can't be 0 because it shoots off, they call this an asymptote. And then we also see that y is not going to be equal to 0, that you can't get y equal to 0. We see another asymptote there. So the domain and range in this case are the same thing. Bigger. How about this one? Well, if you put in 3, 3 squared is 9, 9 minus 9 is going to be 0. But also if you put in negative 3. So one of the things you want to do here is you want to actually factor the denominator to x minus 3, x plus 3, and you see that there's two values that we need to take out of the domain. So in this case, we take out both 3 and negative 3. Interval notation, we say, okay, it can be any number except negative 3. So we can go from negative 3 to 3. Notice the parentheses, we're excluding the negative 3. And we can go any number between negative 3 and 3, but not the endpoints. And then once we get bigger than 3, we can go to infinity. And then the range again is, the best way to take a look at the range is to look at the graph. And we see that basically we can get any number in the range except for 0. But the range is not something we can really calculate. Okay. This one, again, we want to find what is the domain and the range. Well, the domain actually, because there is no problem, right? There is no square root here. There is no division by x, so that we can't have division by 0. So the domain here is going to be all real numbers, negative infinity to infinity. The range, though, again, we're going to have to take a look at the graph. So let's do that. X squared plus 2x. Minus 5. We could kind of see it's going in both directions forever, but it's got a sort of a minimum value here. The y value of negative 6 is the lowest value, and then it goes up to infinity. Now this one is included, so what we're going to see is we're going to get a bracket here on negative 6 when we talk about the range. So domain is all real numbers because it doesn't have one of the problems. We had to look at the graph to figure out that negative 6 was the smallest y value. It is included. Negative 6 is one of the y values, and then it goes up to infinity. So that's range, domain and range. This one we have two problems. We have possible division by 0, so we can't have 9, right? And then we have the top part that could potentially become negative. So we want to keep the top part greater than or equal to 0. So x minus 2 has to be greater than or equal to 0. If you solve that, add 2 to both sides. Our domain x has to be greater than or equal to 2. However, we also have to exclude x minus 9 equals 0, so that gives us 9. So that means we can go from 2 all the way to 9. We can't include 9 because that would give us a division by 0. After we get past 9, we can go to infinity. We cannot use anything smaller than 2 because if we did that, this square root would become negative. And then if you graph this, you'll see that the range is actually all real numbers. And again, let's just kind of do a quick graph of that. use Desmos, you've got this. There is a square root key here, x minus 2 divided by x minus 9, not 0, 9. And so we do see that we can't be anything less than 2, and then we can't be equal to 9, but see 2 is included. This comes down here. So yes, all y values are included from negative infinity to positive infinity. Okay, domain and range here. Well, okay, x is not in the denominator, so x can be anything. Negative infinity to positive infinity. In this case, it's just a number. We're dividing it by 9. What we're going to see is whatever input we have, we could have negative inputs, positive inputs, 0 input, that it will also, and again, you could graph it, but you'll see that the range is also from negative infinity to infinity. You're just taking a number and dividing it by 9. That's all that's happening. In this one, we can't let the inside become negative, so we said x minus 4 has to be greater than or equal to 0. Solve for that, x has to be greater than 4. So there it is, x has to be greater than 4, solving this inequality. And with interval notation, that gives us that we start at 4 and go to infinity. And again, you could also, go back, you can take a look at the graph and you'll see that the y values start at 0 and go up. Each one, but the range, you always have to really look at the graph. So this one we can see, now you'll see x minus 5 cancels, so you say, okay, that's not a problem. However, when we graph this, I'll show you. What happens is we actually still get a hole in the graph at that place. So let's go f of x equals x times x minus 5 divided by x minus 5. Now it doesn't look, it looks all fine, but watch what happens is I trace along here and I get to 5, when x is 5, it says undefined. There's actually a hole in the graph. It doesn't really show up until you try to click there. It's undefined. Okay. So our domain, we still have to keep it out. When you look at it, it looks like, well, it'll take the range will be all things, but let's see, if we get at 5, I think we're going to have one little, because we have that hole right there, 4.98. I think that should be 5.02, 5.01. I think that should be about 5. It should have been 5.5, right? That's really what it comes out as. It's x equals x. So 5 is actually not going to be in the range either, because it's that hole. And then we got this line, right, that just kind of goes up and down in both directions. So what we do is the domain excludes 5, and since the range is also missing the value of 5, the range can be everything except 5. So that's a little tricky one, because you look at the graph, you can't see it until you try to trace over it. So on these ones, again, they give us a graph. We can see the domain goes from -4 to -1, and then there's this break. We go from, looks like that must be -0.5 to +0.5, and then there's a break, and then we go from 1 to 3. -4 to -1, -0.5 to 0.5, 1 to 3. So that's your domain. The range, we kind of do the same thing. We start at the bottom. It looks like it includes -3.5, but it's a horizontal line. That's all that's there. And then we get to this point, which is -1.5, and then it'll take on all these values all the way to y equals 0. And then there's this sort of break, right? And then it goes from y equals 2 to y equals 6. So that's how we write the ranges. They're putting parentheses here, so I guess what I would say is there must be open circles at the ends of these. It's not a very well drawn graph. I would have assumed, if you don't see open circles, I say assume that it's a closed circle, so I would have put brackets here. But if they wrote it this way, we really should have open circles here. Okay, and now we're into 3.3, so I'm going to take a little break here so that there's a separate recording, and we'll move forward.